This video can be used to help explain how we perform the initial installation and adjustment for the optical feedback system we use for the NIWA tracker. So I'll just identify some of the main components. So, obviously clearly this is the Brooker 125 up in our Brooker building at Lauder. It's a near-infrared instrument. We've got a tower supporting the NIWA tracker above. We've got the solar beam coming in here, as you can see, and it goes down and is reflected by the 45-degree mirror here, which directs the beam horizontally into the Brooker. Some of that beam is picked off by a small mirror which feeds the optical feedback system. These are the adjustments for that mirror, and we'll look at it in a bit more detail, but essentially there's a beam coming down, a small pick off, and it goes through a small telescope and then is focused on 4 diodes, which is sort of more towards the floor here, so just out of view. We've got a Linux laptop running the solar tracker program, and behind the laptop's the electronics that controls the tracker. We've got a solar image on the wall here. Now this is off another optical feedback system which we can use. This was one of the original designs, but it's a useful reference, and in fact sometimes you can even see if there's a sunspot on there, you can see how focused things are. It's just quite useful. Another useful feature is this Perspex acrylic top, which is on this sort of source chamber, and that way we can actually look at the aperture of the instrument and actually confirm that the solar image is correctly centered on the aperture. Another really useful feature, which hopefully we can see, is a small little pick-off mirror here, and what it's doing is it's taking a small sample from the sun and it's shooting it against the wall. It's going to be pretty hard to see. Where is it? Probably have to block out various bits. There it is there. You might just be able to see it here. So a really small chunk of front surface mirror, and it's directing the equivalent of a pinhole image on wall about 5-6 meters away, and that's a really good reference because it's completely tied to the instrument. This just demonstrates that spot on the wall, a little glint off a small bit of front surface mirror, how you can outline its position, say with a bit of black felt pen or something, and just walk in and at a glance you can see if things are more or less on target. It's a really useful tool, and if I interrupt it you can see here. You can also look at it and instantly tell if there's cloud passing in front of the sun. So before we make a start, I really want to emphasise it's important to have the solar tracker correctly levelled and aligned, and this procedure is well described in the solar tracker manual. If we don't have it level and aligned, it just makes the feedback system work a lot harder. It also means that on cloudy days it won't track dead reckoning mode particularly well, and it means when the cloud disappears it quickly achieves lock if everything is aligned correctly. However, I will say that the optical feedback system does compensate for poor alignment of the solar tracker and poor levelling of the solar tracker, but it's a really good idea to start with the tracker level and aligned correctly. So we'll move on now to perhaps just showing you the components of the optical feedback system in a bit more detail. Here's the top of the optical feedback mechanism. So firstly we've got this little sample of light that we've picked off as part of the solar beam, picked off by this small mirror here, 10mm by 10mm prism mirror.
So that's projecting that sample down into the telescope. This mirror is adjusted by this kinematic mount here. We have some very nice vernier controls on this particular adjuster from Newport. Here we have a little bit of front surface mirror, and it picks off that little wee extra sample that's sent across to the wall, acting as a pinhole camera. So you can perhaps just see that there. It's a little bit hard to see. On the instrument itself, this is just a little 3D printed stock just to reduce the intensity of the solar signal on the going into the instrument on the aperture. So yeah, 22 millimeters was a good size for us here. It gave us between about 15,000 and perhaps 10,000 counts on the DC level of both diodes detectors. Here's the telescope which takes that sample, focus it with an objective lens there, and there's a Plossl eyepiece there. Focus is fixed, and there's a preamp for the 4 diodes which live down the bottom here under this sort of like baffle, which just keeps a bit of stray light out. The diodes are on a printed circuit board, we'll see shortly, and there's some cutouts in the printed circuit board which just help us set things up. We have this up and down, left and right diode pattern there that we can work out which is which when we're centering. It's just another useful reference, as is this piece of white A4 paper we've got taped to the floor, particularly during the time that we're setting things up. We'll show you the diodes. This is a prototype system, so some of them have the printed circuit board screwed on. This is on a mount just held in by friction, but here you can see the 4 diodes. You can see the cutouts for the up, down, left, right graphics on the floor. Here you can see a focused image of the sun. Actually just determine a bit of cloud going through. There's also a bit of sort of chromatic distortion on this lens. It's actually not the right sort of lens, but it works fine. If there's some sunspots on the sun, with it being so well focused, you can certainly see the sunspots, so that's a pretty good indication things are good. And so what we aim to do is, by looking down through this baffle and looking at the signals, we aim to just illuminate the edge of these 4 diodes evenly. And although hard to see here, there's actually 3 very small holes next to the diode. And so when we look at this reflection down here, we hope to see 1 or 2 of those little holes illuminated. You can just see here, for example, here's 3, here's 2. That just proves that we are more or less centered on the diodes. It's only a rough guide, but it helps with the initial setup. Obviously, as we move the printed circuit board further in, the image gets smaller and we'll see less of these spots. But that indicates being pretty well aligned. But even after doing that fiddle, we'll have to go through the process of just double checking that we've got everything right, and maybe a minor adjustment on the pick-off mirror adjuster. So once the tracker is correctly aligned and leveled, you've basically got the system running. What we want to do is make sure the beam coming down from the sun is perfectly aligned, or perfectly straight up and down. And the way we do this is we'll essentially just back reflect using an oil bath. So just some fairly slow oil, and we'll shine a little spot of light from the sun there, and we'll shine back up at the target. And in this instance, I've still got an old optical feedback system here, so I've got a little device to bridge that, but your system could be different. We need to make sure we get the spot in the centre of the oil, like that, and I'll just go and put in a little masking device at the top of the tracker now, which will produce that spot. Here we have another simple 3D printed part with a little bit of white paper that I can project the image back on itself. Small hole, I don't know, maybe 3mm in diameter. And we'll just put this as high up as we can under the tracker. So I'm standing on a little step ladder and I'm projecting a little image of the sun, and it's going down to my oil stand here, and I'll put my bottle of oil there. You'll see it's nicely centered. If it's off to one side like so, it won't reflect back evenly because of the meniscus of the oil. And now looking back at the top, if we just zoom in on there, you can see it's not perfectly reflecting, so that means we need to move our tracker mirrors, and we'll use the commands on the screen to do that. Okay, so we're on the laptop now, and we're going to just move the mirrors, but before we do that, I'll just point out that we have 0 and 0 in the elevation and the azimuth optical errors, essentially, is what the figure is there. And we've also got the enable feedback deselected, so we don't get any of the movements coming from the tracker itself. The tracker's still working, but it's not receiving inputs from these diodes, which are clearly not illuminated very well because we've got an oil bath in the way. So what we now need to do is simply look at the reflection from our oil up and under the tracker, and then we'll just hit these buttons. I won't say at random because there really is no correlation that's obvious. You could actually make some marks under the tracker to indicate what direction works best. I should mention that the cycle time is sort of in the order of a second, so if you can store up too many commands you'll overshoot. And here they are on the screen, just to remind you what you last put. And I'm just going a few minor commands up and down now, just to finish centering. And I've probably pretty much centered that image, so we'll have another look at it. But before we do that, we can see that we've got some error offsets now. They're fairly small, but they are in degrees, and obviously, 0.04 is, a tenth of the diameter of the sun, roughly. So you can see that they are significant. And 0.08 is quite a bit. So what we'll do now is we'll save the offset. So we'll go save, and it will prompt us yes, and it's saved them to the overall offsets in the configuration file, and it's zeroed the the moving ones as such. So we're all ready now just to have another look at what the reflection looks like. And here we have it pretty well centered. So I think that's good enough. We can say that the beam coming down from the solar tracker is vertical. So with the beam now vertical, it's safe to remove the oil and a little spot of the masking spot under the tracker, and look at the image on the aperture. Now in this instance I've actually vented the instrument and removed the perspex just because it's easier to video than it is just with the naked eye. But with the perspex you actually don't need to vent the instrument. So if I just get rid of some of the illumination by putting my hand, you can see that it's not particularly well centered. The image probably looks worse than it actually is in reality because we're looking at an angle. But really the only way of telling is to choose a larger aperture, and 4mm works quite well. Also, we've taken the perspex cover off, and that affects the weight distribution of the instrument and its springs. So you actually have to put the cover back on to get it reading correctly. In this instance, I've poked the cover just at the far end, so it's more or less correct. So if we go for a 4mm aperture, the hole size almost matches the image of the sun, so it makes it a lot easier to get this thing centered. Still doesn't look great, it's obviously slightly off, but if we attenuate it with the hands slightly, make a slightly better image, you can see how far off it is. Now the only way we can correct this is to make adjustments with the main 45 under the tower. So I'll do that, and as we look at the effects, you can see that's one axis and that's the other axis, and now it's effectively centered. You can see that again, it's just my hand. So we're now nicely centered, and I can sort of prove that. I can bias the instrument by putting some weight on the springs. You can see how the solar image moves around. So yeah, trust me, we're nicely centered. So effectively we've got the tracker axis co-aligned with the instrument's axis. So everything's okay. We haven't involved the optical feedback at this stage. That's our next port of call. We'll now align the optical feedback for this exact situation. Now we need to fine adjust the mirror adjusters that will steer the image to the centre of the diode. So in other words, we want to balance up and down and left and right pairs. You'll see that the optical feedback is not enabled. We'll do that. So we'll go to our mirror, which you can't see. Firstly, we'll get up and down adjusted right, very small movements, and a little bit of a pause to let it stabilise. So there's up and down roughly right, and left and right. When we get them close, eventually it should lock. There we are, locked, depending how your parameters are set. So let it sit there for a little while. See how the inner numbers, the non-bold numbers, that's the sort of 10 sample average. They're the ones you really want to look at. But you can see that left and right pair is pretty close, and the up and down is pretty damn close. Probably could be improved. Let's just watch a little bit more. Unfortunately, actually the sky isn't perfect today. There's the odd passing cloud. So that's probably almost close enough. And when we're happy there, essentially we can tick enable optical feedback, and now the system will make these really minor changes itself and immediately achieves lock. And then essentially the system is now aligned correctly, but we'll probably want to go over to our little reference that we projected on the wall, maybe draw an image around the perimeter of that. Just it's moved, I can see from here, a fraction, because we have made some minor adjustments. Plus I'm going to do this whole process again with the instrument correctly evacuated, and so the lid weight is correct. You can see how stable that looks now, so it's all pretty good really. Just some other minor points. Just remember when you're making adjustments to the mirror, pick-off mirror, just make sure you've got this deselected so it doesn't undo the adjustments you've made. Don't worry too much about getting this exactly balanced. It's a lot finer adjustment than really you need. Obviously, once we enable feedback like this, it'll lock really fast. I should have also said, when we were originally trying to get the beam vertical, these buttons here do a much bigger change than what the program does. And in fact, if we zoom out and just look at now the offsets, you can see that they're actually quite small, 3 zeros, 2 zeros in there, and yet if we go back to here we'll see that it's now locked. That's pretty good. And if I looked at the aperture, I can assure you that it is actually nicely aligned on the aperture. We'll look at that in a tick. Another point is, if you do this, obviously make sure it is a clear, fine day, preferably still as well, because that blows the tracker around. Take a look at these figures. Like around midday, these values are looking like around 250, 300. So we need to set our threshold settings and deadband settings, something sensible. So if we just go back to the program and we look at settings, we'll see what they're set for. Okay, so deadband down here set for 40, it's not bad, and threshold is set for 130. So in other words, that means in the early morning the signal intensity is unlikely to be 300 counts. It's probably more like 200 or maybe 150. So yeah, 130 is okay. Depends how sort of dusty and humid your sky is. The deadband 40, yeah, sort of around something like 10, 20, 30% of the the signal value that you expect at midday is pretty good. So those settings appear to work well with this. And back, we're locked. We'll go and see what the aperture looks like. Here we're looking at the 4mm aperture with the solar image just nicely filling the centre. So it is well centred. Remember that the aperture disc is at a slight angle, so you do get this sort of optical effect where it always looks brighter on this left hand side because you're looking at the illuminated edge. So just bear in mind that you shouldn't bias it. Just by seeing that effect, you actually do want to have it completely centered up and down, left and right. You can test it a little bit by just moving the instrument a little bit up and down, left and right. Again, it doesn't show up very well on the camera, but you can actually see that yes, we are nicely centered. So that's looking good. We're now on the 1mm aperture, and clearly it's going to be hard to see, but what we'll do is we'll just focus in on there, and I'm using my hand to attenuate, and clearly we're centered well within the solar image, so that looks like a success. And the further confirmation is looking at the projections on the ground. You can see these two little dots, so about 1.5 dots, 1.5 dots, 1.5 dots, and 1.5 to 2 dots here are illuminated. Again, it's just a rough indication that the image is centered on the 4 diodes. And finally on the wall, our little glint. It's moved a little bit, but we've made some big changes. But we can clearly see that, this is roughly, equivalent to the solar image. And we haven't changed much from how I had the tracker and feedback system aligned, several weeks ago when I was last playing with it. So we can, probably draw another outline around there later and use that as our new reference. And finally, this is the result of having the tracker well aligned, the optical feedback turned on. Here's SG fit on our plots for what was obviously a clear day. it retrieves pretty much a straight line. There's the odd little glitch, obviously some clouds got in, something's happened, but generally straight lines. So that proves the benefit of having a good tracker, good alignment, and using optical feedback.